All right, name, Daniel Carrera, and thanks to organizers. Boom. Moving on. So I want to begin by laying out the problem that I'm trying to solve, which is the existence of short period planets, by which I mean planets with over periods less than 10 days. Now, we believe that protoplanetary disks are like probably truncated at around the point where the disk co-rotates with the star's rotation period. Here's a plot of the rotation periods of FGK stars in the Orion Nebula, and you see there's a large peak around 10 days. So there's some spread, but it's mainly 10 days or so. So if that is any indication of where the disk is truncated, then why the heck do we see so many planets that are quite a bit closer to a star than that? Um, so I'm going to argue that these planets might form through the migration of long chains of planets locked into mean motion resonances. The general idea is like stay. That if you had just one planet, it would migrate by type 1, get to the edge of a disk, so stop right around there, and that would be it. But if that planet is part of a chain of planets, if it has a companion planet behind it that is locked in a resonance, once the inner planet gets to the edge of a disk, sure, that planet might not feel any more torques, but it's locked to an exterior planet that still does. It's still embedded in the disk. So the other planet can push the inner planet past the edge of the disk. If you have many planets in a long chain of resonances, you can actually move well past the edge of the disk. And so what I want to do here is to try to test that idea, see if it works. And by that I mean, does it produce planet properties that are similar to what we see in Kepler? And that is my contribution to the topic of challenges. Well, how do you test ideas like this against Kepler? And it's actually annoyingly difficult. Planet formation is complex, it's messy, it's a multi-physics problem. There's migration is difficult, there's probably accretion, instability, and all of these things probably matter, and all of them are hard, and all of them are not fully understood, and the only thing you have to compare them against is the final product. Worse yet, although from Kepler we get a large number of planets, for any one planet we have actually quite little information. We have a period and we have a radius, kind of a radius. It's a radius that is itself fairly uncertain, and those missions have a whole lot of fairly complex selection biases. So let's begin with the Threepart formation. So the first thing I spent a lot of time worrying about is exactly what physics to include. I want this simulation to be as meaningful as possible. Yes, of course, there's a trade-off between computing time and accuracy, but even beyond that, even if I had infinite computing time, I'd have to worry about whether a model is so complex that if things don't work, there's no way that I'll figure out which part didn't work. On the other hand, I don't want a model that's too simple because then I worry about whether I'm testing anything at all. And I struggle a lot with that question, and I'm not going to claim to have an answer. I just tell you what I did in this particular problem. So in this case, I'm going to run simulations that have fallen bodies, so it's built on Mercury. So that part is done correctly. There's a 1D disk it's an evolving one-dimensional disk. It has disk torques, and that's it. So you can there are a number of things that aren't included, but that's what I'll try to work with at this point. So let's run through an example. So I'm going to show you a movie of a typical simulation. So here, this is a map of the disk torques, and inside that black boundary, the core rotation torque dominates over the limb torque, so planets want to move outward, and outside here, limb dominates, so planets migrate inward. I'm going to start with, oops, mouse. So I'm starting with 125 planetary embryos. There's inclination, there's over period, there's planet mass, torques, and so initially, the embryos interact strongly with each other, they collide, they grow. Eventually, they reach accessible masses, so they get to the edge of the disk, they migrate. You see already, you have two resonant chains. You see how the inner chain has moved past the edge of the disk. Notice how here, there's no, you have a combination of planets that want to go outward and also want to go inward, and they're kind of fighting with each other. So that's that. And here you see how we've pushed, we've actually moved several planets passing the edge of the disk. Disk went away, so the damping effect of the disk has gone away. The system has become unstable. The outer chain has already collided, and very soon, boom, the inner chain has as well. And we can stop it there. So I run this for, I think this case was for 50 million years. And that's an example. So I do this a few hundred times. And so we have a population of final planets, have orbits, inclinations, and or the order parameters. And I want to use this to compare against, in this case, Kepler. Okay. Move. So here's a tip. If you want to do something like this, if you want to test your simulations against Kepler, do not try to reverse Kepler biases. It's really hard to do, and you'll get it wrong. Basically, I think everyone will. If there's one thing that I've learned from the statisticians back up in State, is that the problem is really hard to do, and nobody gets it right. What you want to do instead is forward model the problem, that is, take simulations and simulate Kepler effects on top of that. Basically, it's easier to break things than it is to take Kepler and unbreak it. So that's what I suggest, and that's what I've done. So first, there's the geometric effect. Planets have some probability of transiting. That's basically a function of the overall distance. That's the easy part. All we can do is you can observe a planetary system from a few thousand different directions and see which ones give you transiting planets. The more difficult effect to model is the detection efficiency of the Kepler instrument itself. That has to do with the stellar noise, the transit depth. The same planet might be detectable around one star upon another over a period as well. If the more transits you have, the higher the probability that Kepler will detect it. And this is probabilistic. The same planet, if a planet is near the threshold, it might be detected or it might not. And you need to deal with that. So here's the first test that I think is one of the more important ones. This is a histogram. It doesn't look like a histogram. This is the occurrence rate of planets, small planets. This is just from 1 to 2 Earth radii. And I chose that range so I don't have to worry a lot about atmospheres. I didn't want to model that. So here we have the occurrence rates. The X's are the Kepler occurrence rates. The colored dots are the predictions from simulations. Blue dots are based on the assumption that the planet is just a bare rocky core, and so that it has the smallest possible size that is consistent with the mass from the simulation. And for for planets beyond 10 days, I also try assuming that the planet has the radius of Jupiter. Um, the reason why that matters is because if a planet is larger, it has a larger transit depth, it is easier to detect. So the difference between those those two dots, the simulations are exactly the same. I haven't done anything different. All I've done is I have painted an atmosphere, a Jupiter radius on top of the exact same planets with the exact same observations, and that's what gave rise to that difference. And here you can see why it's so annoying to deal with these biases. The difference between the blues and the reds is exclusively the selection effect due to the Kepler spacecraft. But in any case, at least here I tested the range from reasonable smallest possible radius to reasonably largest possible radius. And you can see that for the most part, the Kepler data is near there. Clearly, I have a problem here. I'm not getting enough, I'm going to call those ultra short period planets. I think that's okay, because we know that's when there's solar physics that probably matters that I didn't include. We saw that some disks do have the inner edge much closer to the star, so maybe that's what's happening there. Stellar tides, perhaps. Your guess is as good as mine. But other than that, it seems to work fairly well, I will claim. Is there water here? Okay. No. The next thing I tried is, here I'm looking at the period ratios, not between neighboring planets, but between any pair of planets, either where both planets are inside, or one is inside 10 days, or one is inside and one is outside 10 days. It's not what we usually do, but this is statistically a more robust measure. Broadly speaking, it looks all right. I think the biggest problem is my simulations don't produce enough very compact systems compared to Kepler. So I think it's fair to say that that's not working. But other than that, the period ratios are in the right ballpark. Now, I'm talking about a follow-up work. It's based on new simulations, but they're very similar to simulations I just showed you. Now I'm going to be counting the number of transiting planets per star. So in any planetary system, there will be some number of planets that are formed. They may have mutual inclinations. Some subset of those planets will be transiting. Out of the ones that are transiting, a subset of them will actually be detected. So I need to model that. So I take a system, I observe it from a few thousand different angles. For each direction, I get a list of planets that transit, and I run through all 2 to the n possible combinations of planets that you might detect. So you have a system that has 4 planets, of which 3 are transiting, of which only 2 get detected. And in that case, you will count that as a 2-planet system. So if you have 3 planets that transit, there are 8 possible permutations of things that you could find. And so I compute the probability of each one of those and add that to the count. And from that, I get these histograms. So the height of each bar is the frequency of planetary system. What's that? A cough, sorry. So this is a histogram with a frequency of planetary systems that have 1 detected transiting planet, 2, 3, 4, and so on. This is for 2 sets of simulations. The first set is a relatively higher mass system. Here, the initial embryos have half the total mass as in that set. and you see there's a large number of single transit systems. That's the capital economy. As a quick reminder, the capital economy is an apparent excess of single transit systems compared to what you would expect if you took all of the multiple systems that we observe and like just reorient them and observe them from different angles. Um, so the excess is in part due to the fact that there's a distribution of simulation outcomes. Some systems are dynamically hot, have high inclinations, others just happen to be flatter. So the ones that we perceive as multis tend to be from the cold, flat tail of the distribution. But most systems are actually dynamically hot, like the simulation that I showed you. Notice that the capital economy is quite a bit higher for the low mass system than, for the higher mass system. Part of that is formation. Part of it is that they really do legitimately have fewer transiting planets, but part of it is purely a selection effect. It turns out that if you make planets small, if you make planets hard to detect, you will measure a higher frequency of single systems compared to multiple. And that's just the way the probabilities work out. So the capital economy is a combination of, seems to be a combination of different systems have different initial conditions, different masses. And it's a combination of selection effects versus real physics. The dark bars that you see here are the fraction of systems that have detectable transit timing variations, or TTVs. So if I had only this model, you see that that's producing way too many systems with TTVs compared to the total number of single transits. And here I have the opposite problem, where I have too few systems that have TTVs compared to the number of single transits. And that kind of makes sense. I hope it makes sense that more massive planets are more likely to induce TTVs. It's set by the planet to star mass ratio. So it's not, I think, not too surprising that TTVs will be correlated with planet mass. What surprised me more was that the height of that bar was also related to planet mass. So what I'm going to do next is I'm going to blend those two models. I'm going to add them half and half. So imagine a universe that's one half of that and one half of that. The emitting ratio, I chose the emitting ratio to make that orange bar match Kepler. So if you do that, so if you blend models A and B intentionally to make that bar match, then it turns out that that one also looks pretty close. So I think that's an argument that maybe this is, I call that success. So it's interesting that I can make two things fit by tweaking one parameter. Actually, I would look at it more than that, because the height of the solar bars also look similar. I didn't have to be. That could have been, in principle, that could have been some other distribution. So that works. That looks pretty good. What doesn't work is, so here I have rescaled all the bars so they all go up to one. So I'm highlighting the fraction of systems that have TTVs. And so although that looks pretty good, everything else looks pretty bad. And the more multiple the system is, the worse the problem gets. So basically, I'm predicting way too many TTVs for multiple transit systems, and I don't know why. I don't know if it's physics or if there's something wrong with the way I've modeled selection biases. And so, 10 minutes for questions, right on time. In summary, I think that this migration of resonant chains is a promising model for the formation of closed-chain supererrors. It seems to get a lot of things right. It gets the overall period distribution quite right. Mostly the paper ratios look okay. It doesn't produce enough of the ultra superior ratio systems, so it doesn't make as many compact systems as I need. The transform multiplicities look pretty good. It produces the Kepler economy without invoking any extra populations of truly single systems. The TTVs look fine for the single transit systems. I have too many TTVs for the multis. And that's where things are. Thank you for listening.
Thanks a lot. Yes, a question there.
Is Daniel Tamayo still here? Because he could probably ask this question better. No, all right. How sure are you that the endpoints of your multi-planet simulations are dynamically stable for a gigayear or more? If the systems that show TTVs are, other things being equal, are likely to be closer to resonances, which could cut either way. But
good question.
There have been people who have tried to come up with stability predictors. Daniel is one of them. That's why.
Good question. I thought of that, and that's what I hope to do next, because I suspect what you're thinking, that maybe some of those aren't stable. And if I were to run them for a gig a year, then maybe that might fit my TTV problem.
Yes.
When Vlad and I did this sort of game with Brandon Horn in 2012, we found that turbulence in the disk often would break these resonant chains. So I'm wondering how much of an effect that's going to have. Basically, it just gives you random jitters from turbulent density fluctuations. And these resonances are pretty high order, so they're not that big, they're not that deep. And I was wondering if that's going to change the behavior. Now, we were working with a migration trap, so we had longer to disrupt the chains. So as you move in, how much disruption could you get, and would that change the properties of your system in an interesting way?
I haven't thought about that. Good question. I don't know the answer.
Okay,
but
we could discuss further.
It sounds like a really good follow-up.
It's not too hard to add, given what you have.
Yeah.
To it?
Microphone?
I thought the microphone wasn't. All right. So Konstantin Batygin from Caltech, he calculated the criterion for the resonances to be broken by turbulence. So you can add that to the calculation.
Yeah. So I guess if you break a resonance, then the next will be either you're trapping the another resonance, or you collapse, or you hit. Yeah. So.
Yes, Phil.
There was some discussion earlier about the possibility that many of these close-in systems really have relatively modest water fractions. So I'm wondering if you could say something about composition and whether that would be consistent with this migration picture.
Oh yes, I mean the ice line is way far away. So like all the embryos in my simulations were well inside the ice line. So I mean like my enormous embryo was at 1 AU. At this point, for that disk model, at that point in time, the ice line is at like 5 AU. So yeah, there's plenty of room for that.
Okay, other questions? No? Okay, in which case, let's thank Daniel again.
Thank you for listening.